We previously examined discrete probability distributions such as the binomial distribution. Suppose 20% of Americans say they're fine with social media sites collecting personal information on their users. If 15 Americans are asked, let random variable x represent the number of Americans who say they are fine with social media sites collecting personal information on their users. So I give you the graph here that represents that binomial distribution. Remember that n is 15 and the probability of success is 0.2. So any single person they choose has a probability of 0.2 or 20% of saying they are fine with the social media site collecting information. Now what we want to focus on is the idea of discrete probability distributions. Discrete means there's a countable number of outcomes. The only possibilities, if you were to choose 15 Americans, how many of them could say they're fine with the social media site collecting information? 0, or 1, or 2, or 3, or 4, all the way up to 15. We can't have 2.3 people or 7.68 people say they're fine with the social media sites collecting information. So across the bottom on this x-axis, you have the integers starting at 0 all the way to 15. And what you notice here is that once you get past about 9, the probability of exactly 10, 11, 12, and so on is very close to 0. So because that p-value, that probability of success, is so low, that congregates your probabilities down near the left-hand end of the distribution. Okay, notice that going up the side is the probability. So if we answer number 1, find the probability that x equals 3. Remember, as a sentence, what that would mean is if you chose 15 Americans, because n is 15, find the probability that exactly 3 of them said they're fine with social media sites collecting personal information. We can use the binomial formula or our calculator functions, but that's not what we want to focus on here. We want to look at the graph and just kind of estimate our answer. So if we look at the probability that x equals 3, it looks like the height of that bar is at about 0.25, which represents right around 25%. Okay, so 0.25. The second question, the probability that x is less than 2. So again, if you choose 15 Americans, what's the probability that less than 2 of them say they're fine with social media sites collecting their information? So x is less than 2 means x could be 0 or 1. Well, 0, we can estimate that to be right around maybe 4% or 0.04. And then 1, it looks like maybe it's around 13% or so. And again, we're just kind of estimating that. We add those together and get about 0.17. And again, I do want to point out that if I ask you this on a quiz or test, then you could use your calculator functions to find those answers. But I want to focus on the graph because of what this topic is going to turn into here in a minute. Number 3, the probability that x is greater than or equal to 2. Well, that's the complement of x is less than 2. So this one would be asking you, if you randomly choose 15 Americans, what's the probability that at least 2 or 2 or more said they're fine with the social media sites collecting their information? So if you do the complement, that's 1 minus 0.17, essentially 100% minus your answer of 17% in the last one, which is about 0.83. Okay, so here's the point of why we're looking at this now. So in the above binomial situation, we see that x may only take on a specific value, or values, the integers 0 to 15. It makes no sense to ask the probability of x equals 2.3762. So the x-axis is only the integers 0, 1, 2, 3, up to 15. So that makes no sense to say what's the probability that 2.3762 Americans said they're okay with social media sites collecting information. So the only possibilities for random variable x are the integers 0 to 15 in this case. Other discrete random variables, let x equal the number of yearly visits to a doctor. Same idea, you could visit the doctor 0 times, or 1 time, or 2 times, or 3 times. Asking if you visit the doctor, what's the probability of visiting the doctor 2.74 times? That makes no sense. 3.92 times, that makes no sense. So again, those will be integers starting at 0. And then if x equals the number of phone calls a business receives in a day, same idea. They could have 0 phone calls, or 1 phone call, or 2 phone calls, and so on. Okay, so the next thing we're going to look at is something called continuous distributions. With continuous distributions, random variable x may take on any value on the given x-axis. In the real world, variables such as time, height, weight, etc. are generally considered continuous random variables. They may take on an infinite number of values, so we look at probabilities of random variable x over an interval of values. So the idea there is, if you were to, say, take the time of something. So let's just say, let x represent the time it takes to climb a flight of stairs. So you may take your stopwatch out, measure a bunch of people, and you might get times like 6.2 seconds, 6.25 seconds, 6.318 seconds, 12.42 seconds. If it was me, it'd probably be a minute and a half. But the idea there is that the time has an infinite number of values. So it's not just going to be 0 seconds, 1 second, 2 seconds, 3 seconds. Now granted, when you do hit the stopwatch, it is going to round it at some point. But the idea there is that there's an infinite number of values that time could be. Same idea with heights or weights. Even though you may round the answer when you write it down or collect the data, in theory, and that's what we want to focus on, in theory, those variables have an infinite number of possibilities to them. Okay, so that is what a continuous random variable is. When we look at a continuous random variable, rather than doing a bar chart, so rather than it looking like this up here, what you will generally have is what we call a density curve. So a continuous random variable is modeled by a density curve, or function f of x. The area on an interval between the x-axis and the density curve is the probability of x on that interval. Remember that the sum of all probabilities is 1 or 100%. Therefore, the total area under a density curve must always be 1. And again, 1 representing 100%. If you were to take our discrete random variable, if you add up all those probabilities, so if you were to add up each of these probabilities, they should add up to 100%, which is represented by 1. So that concept is consistent between discrete and continuous random variables, that the probabilities always has to add up to 1 or 100%. So on the diagram here, we have a density curve of x. So rather than using bars, we just have this nice continuous curve representing our probabilities. The probability of an event happening is the probability on some interval. So we start at A and end at B. The area here, so here the blue area, is the probability that x is between those two numbers. So if we get to an example of this, without getting too far in depth, so just suppose you're given this density function. Okay, and let's just say that x represents the commute time in a certain city. Okay, so we're not going to get too crazy here. So you have 0.01 representing 1%, 0.02 representing 2%, and so on. So the one that occurs most often, it looks like right around 40 minutes, has the highest probability of about 0.03. So the idea is, if we just said exactly 40, The problem is the area at 40, so if I just draw like a vertical line right there, the probability of x being exactly 40 is actually 0. And that's because there's an infinite number of values on this graph. So 40.01, 40.032, 40.0012, those are all values on this axis. So the probability of any single value occurring is actually 0, which is kind of weird. Because the idea with a continuous random variable is it's the area on an interval. So let's just say you wanted to look at what's the probability that a commute time lasts between 40 and, say, 60 minutes. Okay, so looking at the area here. Well, how much of the entire curve, so starting down here all the way over here, how much of that curve is between 40 and 60? Okay, you might guess maybe 30% or maybe 35%. So the probability that 40 is less than x is less than 60. So basically saying between 40 and 60 minutes is approximately, I'm just guessing here, about 35%. If you wanted to find the probability that a commute time is less than 70 minutes, so it looks like it's about halfway here between 60 and 80. So from here all the way to the left, I would estimate maybe about 90% of that curve is shaded in. So the probability that x is less than 70 minutes is approximately 90%, or 0.9. Okay, so the idea is going to be is that we don't have a bar that we can look at, where we can just look at the height and then take it off of the graph that way. So there's going to be some different methods that we're going to have to use throughout this content, or this chapter. But that's a basic idea behind a continuous random variable compared to a discrete random variable.